And we have explored so far Max Planck and Albert Einstein. That means only the first two characters. Max Planck, if you remember, with the understanding of the emission of black body radiation only through a quantized version of energy. Albert Einstein giving it a mathematical equation and in the photoelectric effect an explanation for these quantums or packages of energy, the photons of energy, so called by Albert Einstein quantums. Later on, in 1922, I think it was in 1922, Compton was a student he finished his PhD in Princeton and then went to do some experiments in Cambridge under the guidance of Thomson. And there he came with ideas of experiments that could throw some light on the quantum phenomena. And we will look at this experiment in this lesson. And then also, I don't know if this was independent or almost at the same time, but de Broglie also presented his PhD on a hypothesis known as the de Broglie hypothesis, which probably gave the theoretical background to Compton's effect, which I think was already there. So I don't know who is the author of the original idea, but these two minds clarified and simplified and unified matter and waves. That means the wave-particle duality. So this is what we have seen. We remember Max Planck's experiment with the quantation of energy, the photoelectric effect by Albert Einstein. We looked at a simulation to understand what factors affect the photoelectric effect. We understood the problem behind the photoelectric effect. We talked about this. It only depends on the frequency. It doesn't depend on the intensity. So that is something that was new to the classical science, could only be explained through the quantum hypothesis. We looked at the simulation to look at the stopping potential. We understood what the stopping potential was and how we can measure, in a way, the kinetic energy of the electrons by measuring the charge of the electrons multiplied by the stopping potential. And that gave us this equation, which is the full equation for the photoelectric effect, where this W is also called phi, the work function. That means the energy required to pull the electrons from the surface. We saw that simulation. We spoke about the saturation current. What happens if you change for higher frequency? There is a lower current but a higher stopping voltage. This was also explained applying the conservation of energy. So done. And now we're looking at this man. Okay, so 1923, Compton effect. What did he do? He had a source of X-rays where he could measure very accurately the frequency of X-rays that he was throwing at a target of graphite. So he was making these X-rays bounce off that target, and his independent variable probably was the angle at which he places a detector to see what happens with the wavelength, with the frequency, what happened with those wavelengths of X-rays. The classical model assumed that the electrons in the graphite would start vibrating with the same frequency of the gamma of the X-rays. So therefore, the scattered beam should have the same wavelength coming from the radiation of the electrons or the vibration of the electrons, or coming from the reflection of these waves. But that is not what the detector measured. There was a change in wavelength from the original wavelength hitting this target, and that changing wavelength could not be explained with the classical mechanics. So this was a very strong evidence for the idea of light being quantized. So let's look a little bit at these ideas. So this is what he detected. When the angle with the detector was 0, the wavelength that bounced was very clearly equal to the wavelength that hit the target. But then as the angles increased, the wavelengths started showing difference between the incident and the reflected wavelength. Longer wavelength meant less frequency. That means as if there was some energy being lost in the collision between the energy of the X-rays and the electrons. And this has a strong connection, of course, with the photoelectric effect. And this is what the experiment gave, a very strong difference for certain angles, maximizing the change of wavelength. So these are the results of Compton's effect, and we need to be able to explain them mathematically. So let us do this. Let's explain these observations using some equations. If we look at X-rays not as electromagnetic waves, but as these strange photons traveling at the speed of light, that they have a momentum that is not zero, and they have no mass because they travel at the speed of light. If we accept this idea of the photoelectric effect, then we could very easily say that we could use Planck's equation, right? And we know that C is equal lambda times F. So from these two equations together, we could say that E equals Planck constant times C over lambda. Here it is evident that if the wavelength is increasing, then there is a loss of energy. So that means that this photon loses energy when it collides or when it transfers momentum to the electron, right? That is in the target. So this equation would explain this increase of wavelength of that specific incoming wavelength into the target. Now, the second great contribution of Compton is to use special relativity's equation. In special relativity, Albert Einstein stated this equation that connects the energy with the momentum, right? P squared, C squared plus the mass of that particle when it is at rest times the speed of light squared. But this is zero because the proton has no mass, right? So therefore, if we apply special relativity, that means the physics of the big, to the very small, which is what is happening here, then we could conclude that E squared is equal to, okay, let's take out the squares. E equals P times C. And this is also equal to HC over lambda. So this C cancels, okay, let's forget about this. This C cancels with this C, and we have this equation that then became the de Broglie hypothesis. Momentum and wavelength being inversely proportional to each other, and the duality of matter and waves, or particles and waves, started in Compton's head when he observed the results of his experiment. That is what I think, but I'm never sure. I never asked Compton.